Okay, hi guys, once more we continue where we left off the previous week. We started treating Euclidean geometry, and we are continuing from where we left off. If they are, hopefully, I hope they are faithful grade 12 students amongst those of you who are watching. There was a problem that I left, the last problem I left you last week as homework, which needed the application of the theorems which we introduced last week. Excuse me. So if you did the problem, you should have come to some form of a stumbling block or an obstacle, because there were two theorems which I did not introduce to you last week, which you needed for that last problem which I left you with. So unless of course there are students who go on and do and read their textbook or their notes, then they would have solved the problem. But if you solely rely on what we do here, then you should have struggled a bit. So let's start there. So we start there before we move on to polygons and proportionality. So we start with the theorem about tangents. So I call it theorem 6. So I will just read it out. If two tangents are drawn from the same point, so the same point here would be P. So you see, I'm really trying to draw these diagrams. So of course, if I take time to prepare these lessons, it only makes sense that if you are grade 11 or 12, you should take time to do your work after you have seen these lessons. So there are two tangents, AP and BP. So the theorem says if two tangents are drawn from the same point, so they're drawn from the same point P, outside a circle, then they are equal in length. Right? And remember, for these to be tangents, they need to touch the circle at a single point. Right? So these are AP and BP. We certain that they are tangents. Why? Because AP touches the circle at point A and BP touches the circle at point B. So the theorem is that if these two tangents are drawn from the same point P, then they should have equal lengths. Right? Then they are equal in length. So if you want to prove the theorem, what would you be required to prove? You'd be required to prove that the tangent, the line segment, which is the tangent AP, is equal to PB, because that is the main claim of the theorem. Right? The main claim of the theorem is that the lengths of these two tangents, which are drawn from the same point, are equal. So that's the main claim. So this is the, if we were to prove this claim, then we would have proved the theorem. So you know how it works. Proof. So, and look, Euclidean geometry, it's mainly about statements and proofs. So for each and every statement that you make, can you supply a proof for that? In secular terms or in law, they would say, can you supply evidence for that? Right? So you cannot escape it, and it will help you if you just familiarize yourself with these proofs, because when you go to university and you do mathematics, certainly you will be surrounded by proofs. Why? The reason is mathematics is not a faith subject, right? Anything we say, we need to be able to prove. That is what makes it a science. So the proof, and typically you would use theorems which you know already to try and prove new theorems which have been conjured, right? So what can we do, or what do we see here? The first thing we can do is we can construct a line OP. So we construct a line OP. And the reason I'm constructing this line OP, it's because then I will have two triangles. So mathematics is also about observation. So geometry, I mean, is about shapes, lines. So of course you need to be very observant when you deal with geometry. So okay, so we've constructed the line OP. So that's the first thing we have done. Construct line OP. So this is just our construction. We've constructed line OP. So, and this line OP, you can see that you get from OP, it becomes a common side of triangle AOP and triangle OBP. So that's one thing that we have now just by construction. That line is common between the two triangles. And what else can we say here? We can say in triangle A, I want to say in triangle OA, angle, so the angle is at AP, and triangle OBP, what you have is that OAP, so this is an angle, OAP is equals to angle OBP, which is 90 degrees. So I'm not sure whether you can see why, because we must supply a reason. Remember, for every statement we make, we must be able to supply a reason. Why is that angle there, OAP, equals to the angle there, OBP? Why is that the case? The reason is this is a tangent perpendicular to radius. And where is the tangent and the radius? AP is a tangent, OA is a radius. OA is a radius. Why is OA a radius? It's because a radius is any line drawn from the center to the circumference of the circle. And what do we know about radius? Remember, one radius, many radius. Excuse me. OA is a radius. What do we know about a radius and a tangent? Is that they make an angle of 90 degrees. So every radius which is drawn to a tangent, they form an angle of 90 degrees. So a radius is perpendicular to a tangent. So that's why here 90 degrees. What's the reason? Tangent perpendicular to radius. Okay? So those two are equal because OB is also a radius. And we know that the radius will make an angle of 90 with the tangent. Okay, so that's what we have here. And what else do we know? Remember, I said we already know that OP is equals to OP in two triangles. Why? Because this is a common side by construction. Common side. Okay. What else do we know is that OA and OB must be equal, because this is what would make this a circle, and unless this is not a circle. If I draw any line to the circumference, even if I draw the line from this center to there, or there to there, or there to there, all those lines should be equal, because this is a circle. That is what defines a circle. The radius of the circle are equal. So you have that OA is equals to OB. Why? These are radius. Okay. So, and I will just show you on the following sheet. I will just remind you of similarity and congruence. But from here, you have that you have one side, common side. So this OP is equals to OP, first thing to note. And you have OA being OB in this in these two different triangles, and you have an angle also. You have an angle. You have two angles being equal. So these two triangles, so triangle OAP should be congruent. This is how we write the symbol for congruence to triangle OBP. And what's the reason for that? You can say there's a common side being equal, and there's another side which is equal, which are the radies, and you have an angle which is 90 degrees, the one which is formed between a tangent and a radius. Or you can even state the hypotenuse, because this is a right angled triangle. So you can have the reason being side angle, or you can just have RHS, you understand? Right angle, hypotenuse, and the side being equal. So now we have that these two triangles are what? Are congruent, right? If these two triangles are congruent using this side, those two sides, and the angle, which other side is now left out, it's AP and PB. And from the congruence of these two triangles, therefore, we have that AP must be equals to PB. And this is the hypotenuse also. These are the hypotenuse side, I think. But anyway, without even using that this is the hypotenuse, it has to follow, because that side is equals to that side, that angle, that side is a common side. Therefore, it follows, because those three identifications qualify these two triangles to be congruent. Therefore, the remaining side must be equal. AP must be equal to PB. So that's what we have here. So we have proven the theorem, right? So we no longer just believe because we are told, we have proven the theorem. So that's how it goes. So you know how it works. I've shown you the theorem. Let's take an example where we need to apply this theorem, right? I call it example 0, okay? So we apply this theorem on triangle ACE with a circle with points BFD, but you have sides there. So you have BAB. So let's just divide those. So AB is A. That's what we are given. And we are given that from D to C is B, from D to E is C. And we're also given that AE is that side. This is how they denote sides in engineering. So it's that side. So AE is that side. We are given that this is 5 centimeters. And you have AC from there to there being 8 centimeters. And you have CE from there to there being 9 centimeters. And the question is, find the side A, B, and C. So how would you go about that one? So we've just seen a theorem about tangents drawn from the same point, right? And the claim is that they're equal in length. What do we have here? We have a tangent AB or AC, you can think about it as AC, being drawn from the same point A with the tangent AE or AF. Again, you have that tangent CA being drawn from the point C with the tangent CE. Similarly, you have a tangent EC being drawn from the same point E with the tangent EA. Right? So already you can see the information that you have. So what can we say? We know, so the solution, what do we know? We know that AB is equals to AF. AB is equals to AF, which is equals to A. And what is the reason? The reason is that these are tangents drawn from same point. This is just the theorem which we've just proven that it is true. So if we see two tangents drawn from the same point, then what we know is that their lengths must be equal. And that's what we know there. And the length is A. Okay. What else do we know? We know that EF must be ED. EF must be ED, and that is C, because ED is C. And what's the reason? The reason is the same. Tangents drawn from the same point, E. EF and EC, their lengths should be the same. What else do we have? From these two tangents, you have CB is equals to CD, which is B, right? What's the reason? Similar. Tangents drawn from the same point. So you have three equations. 1, 2, 3. Right? So you have three equations, you have three unknowns, A, C, B. Right? But what else do we know from this diagram? We have been given the lengths AE from A to E. So we know that AE is equals to 5 centimeters, right? But what is AE? AE is AF, but we've just shown AF is A, so it's A plus FE, and we've shown FE is C. So you can have this as your equation 1. So A plus C is equals to 5. And from AC, which is 8, we are given AC is 8 centimeters. AC is from that point A to the point C, which is made up of AB and BC. We know AB is A plus BC. We've shown BC is the same as CB, is B. So this is equation 2. And the last equation you get is CE is 9, which is B plus C. So this is equation 3. So when you hear, what do you do? Simultaneous equations. So you should have done this in grade 10. Basically, what do I mean? I mean you have three equations and you have three unknowns. So you have squared up. You can solve this. So just solve this in your own time. And you should converge with an answer that says A is 2, B is 6, C is 3. So this should be your answer. Okay? So I'm not going to work it out here. I'm sure you can work out those three equations. Set A to be the subject of the formula here. So A, so from here, you will have that A is equals to 5 minus C. Why? Because you transpose C to the other side. And you can come substitute A here. And similarly, you can substitute B here or whatever. I mean, it's easy to do. I don't have to take you through that because I assume that you are in grade 12 or 11. So yeah, you've been through simultaneous equations. If not, I will be dealing with functions on my timeline. So rather look out for Sipolukosi. Just check out my timeline. There is a lesson which I will take for functions because I know algebra is very important and some people miss it and we take it for granted. Okay, so that is, so yeah, those are the solutions. So you should be able to work that out from there. But what have we done? We have applied this theorem in solving for sides of a tangent that is touching a circle. Okay, so let's move to the last theorem involving circles, which you need, which is called a tangent chord theorem. Very important theorem, very, very important. So pay maximum attention. And then after we've done this theorem, then you can go back to that problem which I left with you last week, and you should be able to solve that problem armed now with these two theorems. Okay, so what does the tangent chord theorem says? It says the angle between a tangent to a circle and a chord drawn at the point of contact is equal to the angle which the chord subtends in the alternate segment, right? Okay, that's what the theorem says. Okay, I know that was gibberish. Let's go through it slowly. The angle between a tangent to a circle. So where's the tangent? Here's a tangent. You can think about SB. You can think about SB as your tangent, or BR, right? So the angle between a tangent, so let's take SB, right? So the angle between a tangent and a chord drawn at the point of contact. So that's important. So here's the point of contact with the circle. And where is a chord drawn from that point of contact? We can see one chord here as AB. AB is a chord, but QB is also a chord, right? And PB is also a chord. So we have to focus now our concentration here. Okay? So let's take AB. So the claim would be that that angle over there, so the claim of the theorem would be that angle over there, which I call ABS, which is the angle at the point of contact. So this is the tangent, this is the chord, should be equal, is equal to the angle which the chord subtends in the alternate segment. So what is a segment? A segment is one area of the circle which is divided by a chord. So take a chord AB. This area over here is a segment. And that area, that whole area over there is another segment of the circle. That's why last week when I began the lesson on Euclidean geometry, I started with showing you how circles are labeled. So a segment is one part, right? Or one part of a chord. So there will usually be two segments if you have a chord, that segment and that segment. So the claim is that this angle which the tangent forms with the chord is equal to the angle, so here's a chord, which the chord subtends, where? In the alternate segment, no longer in this segment, but in that segment. So which is that angle? That angle which is subtended by this chord AB is the angle Q1. So the claim here is that angle Q1 should be equals to angle ABS. ABS, that angle. And of course, similarly, you can think about the tangent RB, where now you would have that angle over there being equals to that angle, because it's on the alternate segment and it's subtended by this chord. So maybe this might not be that clear. So it is wise that maybe you go through what I've been saying. I've tried explaining it to the best of my ability, but perhaps let's supply a proof. Maybe it will make more sense. So what are we required to prove? We are required to prove that ABR, which is that angle, is equals to APB, which is that angle. So this is the claim. Forget, never mind the fact that I did not draw maybe these angles to scale, that you can't see it visibly that those two angles are equal. But that is the claim of the theorem which we need to prove, right? And that I would do something like that. So as I said, there are two things that you can prove here. You can prove that that angle is that, or this angle is that. So that's what I'm saying here. So ABS is that angle equals to AQB, which is that angle. Okay. So what do we do? The first thing that maybe you can see already from the diagram, so I'll say proof. So we've drawn a diameter already. Draw a diameter BT and construct TA, right? So the claim is that BT is a diameter, not TA. So I'm saying just let's draw BT. This is our own construction. A diameter is a diameter because it passes through the center and touches the opposite side of the circumference. And I'm saying over that, construct TA, which is just a small chord from there to there. Why? Now I have a triangle BAT. Triangles are useful. Okay. So what do we know from here is that angle ABS, which is one of the which is the contiguous angle which we want to show, that is equal to the angle in the opposite segment subtended by the same chord, plus angle ABT, ABS and ABT, so ABT should be 90 degrees. Why? Because the reason is tangent perpendicular to radius. So let's look at that again. So angle ABS is just that part, right? But angle ABT is that, I don't know, I don't have a different colored pen, but ABT, how can I denote it? It's that part, so I'm going to use 3 lines. So it's just that small angle. So we're saying this angle plus that angle should be 90. So that's the claim. So I'm going to put a big 90-degree sign there. So that is the claim, that those two angles add up to 90. Why? Because this is a radius, and for OB, as much as this is a BT is a diameter, but OB is a radius. So a tangent to a radius forms 90 degrees. So that's what we have. What else do we know? Angle BAT, should be 90 degrees. What's the reason? Remember the theorem which we were concerned with last week about angle in a center being twice the size of the angle at circumference. So this is angle at center being 2 times angle at circumference. And because the angle at center here is the angle O, and what's that angle is 180 degrees. So what's half of 180 degrees? It's 90. Okay. So that's why you have 90 there, 90 degrees. Okay. So therefore, we know that this means angle ABT plus angle T should also be 90. So which are those angles? ABT, so it's that angle ABT plus angle T should be 90. Why? Because that angle is already 90. That's what we've shown there. So these two angles must be 90 because the sum of angles in a triangle is 180. So 90 plus 90 should give you 180 degrees for triangle ABT. Okay? So I need your maximum attention. That's if you're still there. Okay? So what does this mean? It means angle ABS should be equals to T1. ABS should be equals to T. Call it T. ABS should be equals to that angle. Okay. Why? It's because these are angles in the same line segment. Okay. So ABS should be T, and ultimately you will have that angle Q1 is equals to angle T, so that angle should be equals to that angle also. See those two angles? It's a theorem we dealt with last week. You see those angles are subtended by the same chord. So those two angles should be equal. Okay? So this will imply that Q1 therefore should be equals to A angle BS. So Q1 must be ABS. And that is what we wanted to prove, because Q1 is also angle AQB, which is that. And Q1 is angle AQB. So we've proven this, which is ABS. So that's what we wanted to prove. AQB is ABS. So we've shown that that angle is equal to that angle using all these theorems you already know about manipulating angles within circles. Right? Very cumbersome, but if you pay maximum attention, it should be very easy for you to follow and to master. Okay? So yeah, then take these theorems. So an example for this theorem is that last problem I gave you last week. So go attempt that problem using these two theorems and see how far you get. Really do it, because really mathematics you cannot learn by looking or listening. You must do it, right? Okay, great. So we move. So following two sheets is just brief reminders of what I expect that you should already know from your previous grades. Remember the old idea of congruence. Congruence. When we say two triangles are congruent, right, and the sign of we depict congruence as, let's say, triangle ABC, congruent is depict like this, is congruent to triangle DEF. And there is a number of cases which qualify triangles as congruent. Right? The main three that we need to look at now, so it's just for you, I'm just reminding you, I'm not going to dwell much on these, is that if you have two triangles ABC and DEF, and you have side AB being equals to side DE, so this is in triangle ABC and DEF, and triangle DEF, AB is equals to DE, because we're given, remember those small sticks, those just denote lengths, that this AB is equal in length with DE, and this one with 3 sticks will denote that BC is equal in length with DF. So what we have here is AB is DE, and you have also AC is EF, right? That side, because these are just given, and you have BC is DF, BC is DF. So you have 3 sides of this triangle being equal, and when this is the case, then we say these two triangles are congruent. Therefore, triangle ABC is congruent to triangle DEF. And what's the reason is that side. Side. So the 3 sides are equal, and this is what makes these two triangles congruent, right? And you can have another case where you have 2 sides being equal and an angle, maybe. Right? Let's say you have that angle. So here you have 2 sides, IL being equals to GI, HI being equals to KL, and angle H being equals to angle K. If that's the case, these two triangles, triangle GHI is said to be congruent to triangle IKL. And what's the reason? The reason is that the 2 sides are equal and one angle, side angle. Same logic for triangle MNO. It will be congruent to triangle PQR. And what will be the reason here? You have 2 angles being equal. Angle M is equal to angle P, angle N equals to angle Q, and one side NO being equal to QZ, so you have angle side. So you have 2 angles being equal in one side. And therefore we say these triangles are congruent, but with different reasons, right? So that's just a quick reminder. Okay. So now we move on. Another reminder on similarity. Well, I'm not sure whether you've seen this before, but there is a related idea to congruence that we call similarity. And similarity is about equiangular triangles. Remember, we have equilateral triangles. which are those triangles. This triangle ABC and triangle DEF. Those are called, well, maybe that's not a good example. I mean, let me just draw it here quickly. If you have all sides of a triangle being equal, and then these are called equilateral triangles, but you can also get equiangular triangles. And if, of course, if you have another triangle with similar sides to this one, these are equilateral triangles. Equiangular triangles is when you have triangles having angles of the same magnitude. So that angle is, so in triangle ABC here, so if you pay attention here in triangle ABC and triangle DEF, you have angle A being equal to angle D, which are both A, and you have angle B being equal to angle E, which are both B, and angle C equals to angle F, which are both C. So you have angle. So three angles of the same or three corresponding angles of two different triangles are equal. Then these are equiangular and they are similar. So therefore, here you will have, so therefore we'll say triangle ABC, and the sign for similarity is then that is similar to triangle DEF. So that's how we write similarity. So the angles have to be equal, or the sides, the proportions of the sides should be of equal proportion. Look, the triangles don't need to be of equal size as in congruence. With congruence, you need sides to be equal, but with similarity, you don't need that. You only need the proportions of the sides of the two triangles to be equal. So if you have MN, over RS being equals to ML over RT being equals to NL over ST, therefore we say triangle MNL is similar to triangle RST. Right? So with triangles, you can move in between, right? I think if you can show this, you should be able also to show this. Or if you can show this, then you can show this. But we will see this in examples. So that was just brief revision. So we move on to some other revision again. So why these revisions? Is because they are very important for polygons that we will just show a few examples of. So now we move to polygons. And what's a polygon? A polygon is a plane closed shape consisting of three or more line segments. So the shape must be plane, but it must consist of three or more line segments. So of course, a triangle is a polygon because it has three or more line segments, and that sort of a shape is also a polygon because it has three or more, and that is also a polygon. So it must just have three or more sides, right? And I always say this is if you those who pay attention to the Christian faith, you would understand that Christians, Jews, and Muslims claim to have a monotheistic faith. So poly is in opposite to mono. So poly is in Greek. Mono means one, poly means more than two, or three, or many. You understand? Many. So Christianity is a monotheistic religion. Mono means one, and theistic from the word theo, meaning God. So Christianity is a faith of mono God, one God. But where Christianity was born in the Roman Empire, and even today, in some parts of the world, there are still polytheos, many. So religions of many what? Gods. So this is monotheistic, one God, polytheistic, many, three or more, or two or more. 2 more, right? So polygons means shapes of many sides. So gons will be side, right? Okay, so quick reminder, triangle, just a triangle. What is the area of a triangle? It's half base times height, right? That's just quick reminder from grade 9. And I've just made some construction there, AD and DB. If you ignore AB, you would see that ADBC is a trapezium. So ADBC is a shape that we call a trapezium. So the area of a trapezium is half A, that length of the small side, plus B, the length of the large side, multiplied by the height. Area of a trapezium. An area of a parallelogram, actually this is not breadth, should be something like length times height or something, right? For a parallelogram, and I showed you a parallelogram last week. And you can also have a rhombus. Rhombus is more like a circle in italics, as much as a parallelogram is more like a rectangle in italics. So you can see a rhombus is defined by equal opposite angles and equal sides. And the area of a rhombus will be given by the diagonals half, the product of the diagonals, half AC and BD. And you also have a kite. So if you are a young man growing up in a location, we used to forge these using sticks, plastic, but we never used to measure angles or sides. But of course, we needed to make it to be a kite for it to be able to obey the aerodynamical laws. But here's a kite, so I mean, this is the shape of it, and the main important thing is that the area also is given as half AC, the longest side of the kite, multiplied by BD, which is just that side which forms the perpendicular angle with the longest side, right? So this is just a reminder, okay? So these are very important. So you see, the education you learned in the previous grades is never useless. Education is cumulative. What you learn will assist in the near future, right? So let's move on. Okay. So now we get to the dreaded idea of proportionality of triangles. So I'm going to deal with proportionality of triangles. And a few principles that you must be aware of with the proportionality of triangles. So I begin by giving you an example of two triangles. So here you should be able to identify triangle ABC and triangle DEF, right? You should be able to identify those two triangles there. But these two triangles are within parallel lines, right? And for the mere fact that they are within parallel lines, their height should be similar, right? They should have the same height. As you can see, we can easily construct a height H there and another height. So height H is for triangle DF, and you can see if you construct another height for triangle ABC, you would get basically the same height H. Right? And this would be a principle, since the area of a triangle is half base multiplied by the height, right? So if you have triangles with equal heights, then their areas will only be determined by the base. They will be proportional to their bases, because these two triangles have equal heights. So if you determine their area, the only thing that would make their areas to be different is the base. So that's one thing that you just need to pay attention to. If you have two triangles within parallel lines, then their height should be similar. And you will see how that is important when we take an example. And the second principle is that here, in this second scenario, you are given basically triangles with equal bases, right? Equal bases and equal height. So here you should be able to identify triangle WXZ, WXZ, so there's the base, So the base is WZ. And you should be able to identify triangle WYZ with the same base WZ. And so look, these triangles now have the same base, but they also have the same height. I mean, if you were to construct the height of WXZ, maybe you would say maybe you can do that. But still, I mean, still, these are within parallel lines. So we expect their heights to be the same. And you can construct the height for WYZ, which would be maybe something like that. And you can see that this would be just same height as H. So what do you have here? You have triangles which have the same base and the same height. And I'm sure it should be, the alarm should be going off in your mind that it means that these two triangles should have the same areas. So that's the principles. Triangles with equal bases and between the same parallel lines are equal in area. Of course, the same parallel lines guarantee that they have the same height. And therefore they will be equal in area. And remember, when we speak about proportionality, as I said I was intro, just reminding you of similarity. Proportionality is about ratios of sides, just ratios. Side MN over side PQ, side AB over side DE. That is basically proportionality, ratios, right? Okay, so let's take an example. So you have here a polygon. And you are given that in this polygon PQTS, you have QR being equals to 30 centimeters. So QR is that side. So that is QR. So this is what? 30 centimeters. And we are given RS 45 centimeters, and we are given H, that constructed height. H is equals to 10, and we also have another height, H, big A, capital letter H, which we don't have. And what is the task? The task is that you must calculate H, right? Capital letter H. So what can we use quickly? Area of PQRS. What is PQRS? PQRS is a parallelogram. And what is the area of the parallelogram? Area of a parallelogram is length times height. Right? And what's the length? Is SR, which we are given to be 45, multiplied by the height, which is 10 centimeters. Remember, we are in PQRS. We've constructed that height, H, right? So the area of PQRS is 450 square centimeters. Simple. And now what is H? Because that is the question, determine H. So to determine H, again, we come back to the area of PQRS, right? The area of PQRS can also be determined using the length of the other side. Remember, I mean, this is a polygon, so it has different sides. So it has that side SR, it has that side PQ, PS, and QR, right? So if you use SR, it's like using PQ. So if you now want to use that length, we need to use that height. If we use this length, we use that height. And if we use that length, we must use that height. So now we can say area of PQRS should be QR multiplied by what? That height H. But we know what is QR is 30 centimeters, and we know what is the area of PQRS because we got it from up there, 450. So simply you say you solve for H here, so H is 15 centimeters. Simple. Okay. So second question is, we are given now the proportions. Now you are given the proportions. You are given that if TR, which is that side, if its proportion to TQ is that long side, is 1, show that the area of triangle STR over the area of triangle PRQ, so those two triangles, is equal to 1 over 3. But you are given something, you are given that ratio. TR and TQ is 1. So let's start with what we have. We have that, no, it's not, I think I captured the question with an error. TR is to TQ is 1 is to 4, actually. 1 is to 4. 1 is to 4. So that's what we have. So then TR, TQ is 1 is to 4, right? So you can also write this as TR, TQ is 1 over 4, because that's what proportionality means. Okay. But this implies that RQ over TQ is 3 over 4. Why? RQ, which we have, right? RQ over TQ. So you must pay attention here. This whole side, so this whole side, TQ, right, should amount to like 100% proportion. What do I mean by that? You have TR, which is 1 part of TQ. So you have TR over TQ being 1 over 4. So what does it mean about the remaining part? The remaining part is RQ over TQ. The remaining part must be 3 over 4. So that TQ over TQ would be 1. So you have so what am I saying to you? If this part is 1 over 4, then this part should be 3 over 4, because you have 1 over 4 plus 3 over 4 being equals to 4 over 4, 1. That's what I mean by 100%. It's a full side. It's full ratio. Its full length is 1, but you are dividing it into ratios. So it will be that ratio over something. So if you have that part being 1 over 4, it means that part would be 3 parts over the whole, which is 4. So that's why you have RQ over TQ, which is 3 over 4 here. Okay. So what else do we know? We know that, therefore, we'll have TR all over RQ being equals to TR over TQ multiplied by TQ over RQ. So I've done nothing here. I've just expanded TR over TQ. TR over TQ, check here. TQ and TQ will cancel each other here. TQ and TQ will cancel each other. You have TR over RQ, still the same thing. But why am I doing this? It's a trick, because I know TR over TQ is 1 over 4. So this is 1 over 4 multiplied by TQ over RQ, 3 over 4. So RQ over TQ is 3 over 4. So TQ over RQ is 4 over 3 actually. 4 over 3. So this would be 1 over 4 multiplied by 4 over 3, 1 over 3. Okay. So I'm going to write here now because I'm running out of space. So now we can go and say, now let's look at the area of triangle STR, which is half TR multiplied by H. Where's STR? STR, the base is TR, right? What is the height? The height is H, because this triangle is within the parallel lines with that triangle. So the height is still H. So the area of remember what we want to show. We want to show that area of triangle STR over the area of triangle PRQ is 1 over 3. So area of triangle STR is that what the area of triangle PRQ, this is half RQ multiplied by H. So if you divide those two, so if you say area of triangle STR over area of triangle PRQ, half and half will cancel, H and H will cancel, you'll have TR over RQ. And we've just shown that TR over RQ is 1 over 3. So this is equals to 1 over 3, which is what we were supposed to show here. That area of triangle STR over area of triangle PRQ is 1 over 3. So that's what we needed to show, and this is correct. We have shown that. So you need to be patient with these things. You need to be very patient. You need to, perhaps, if you are a learner out there, need to go through what I've just done here, right? There is no other way of making it any easier. You just have to follow it and try to do this on your own, right? So that's an example of proportionality. So I guess that's why proportionality seems like a monster, because it has a lot of these detailed proportions that you need to pay attention to, and these kind of principles and theorems that you need to know. Okay. Okay. I move. So let me see. So we are left with only 2 pages. Only 2 pages. Then we are done. Sure, this is taking a toll on you because this is a bit of solid material for you to take in one go. So I know that we are trying to do more than we can, but we trust you that you will do your work after this. Okay. So theorem 8. So I call another theorem 8. A line drawn parallel to one side of a triangle divides the other 2 sides of the triangle in the same proportion. A line drawn parallel to one side of a triangle, so we have a triangle ABC. We draw a line parallel to one side, so let's take a side BC. We draw this line DE, which is parallel to BC. I try to depict it in a different diagram here, right? So where's your DE? DE parallel to BC. So the theorem says a line drawn parallel to one side of a triangle divides the other 2 sides of the triangle in the same proportion. So this line should divide the other 2 sides of the triangle in the same proportion. So which other 2 sides? AE and EC. Right? I guess AD and BD. Okay. So what are we given? We are given triangle ABC, and we are told that DE is parallel to BC. Or you can look at that, DE parallel to BC. Right? So let's see if we can prove this. So what are we required to prove? We are required to prove that basically triangle ABC is similar to triangle DEF and AGH. So I will construct F. Okay. So where do we start? We can also construct the let's get more triangles. And we also can construct perpendicular heights there. So these are perpendicular heights. So how do you go about this? The first thing that you can pick up here is that you have AB all over DE being equals to AC all over DC. Okay? So this we are given. So let's look at it again. AB over DE AB over DE is equals to AC all over DC. I want to say DE. C actually over BC. This should be BC. AC all over BC or DE. So this is given because what are you given? You are given a line drawn parallel to one side of a triangle. Here's one from there to there. And you are told that it divides the other two sides of the triangle in the same proportion. Two sides, so you have AB and AC. So AB, so this is DE. Yeah, so this is true, DE. So this is just given. And what else do you have? You have AB, I will show you now, over AG is AC over AH. So you have AB all over AG being equals to AC all over AH by construction. Understand? So this is what we've constructed. Construction. Right? So you have sides in proportion now. So therefore, because of this, we have GH being parallel to BC. Why? Because of sides in proportion. So where's GH? GH will be parallel to BC, right? Therefore, this implies that angle B is equals to angle AGH. These are corresponding angles between GH, which is parallel to BC. GH, which is parallel to BC, and you have angle B being equals to angle AGH. So it's like, if you have that, then you have that angle being equals to that angle. So these are corresponding angles in parallel lines. Remember, you have those angles which are between parallel lines which are equal. And also, this means that angle C is equals to angle AHG, corresponding angles again. And then ultimately, you have triangle AGH being similar to triangle ABC. Why? Because you've shown that angles are equal, equiangular. You've shown that the angles are equal. And similarly, you can show this for triangle ABC, that it is similar to triangle DEF. Just following this same construction between proportions between sides and using those to get to angles, right? And if you pay attention, last week we introduced the midpoint theorem. This theorem is more like the converse of the midpoint theorem. where the midpoint theorem says if you draw a line from the midpoints of a triangle between two sides, that line will bisect the two sides, meaning it will cut it in half. So these two theorems are converses of each other. Okay, my wife is so ABC, D. I think that's supposed to be DE. Perhaps F is supposed to be there. Let me say DEF. Yeah, there's a common here. F is supposed to be the DEF. Yeah, if you want to show this, then F I think should be somewhere there, and there you have the common line and all that. Okay, so we'll just move from that. So yeah, I mean, of course, what is important is for you to show that, and you can make other constructions where you have F, and you can also show another relation. But that first part is sufficient for you to get full marks. You have proven this sort of theorem, right? So you can just polish that. Okay, so we move to the last part of what we have to do, showing that polygons are similar. So I mean, we've just dealt with triangles. What about more than three sides? I mean, when you have polygons, so as I said, the similarity of polygons will be similar if they are the same shape, but they don't have to be the same size. They can differ in size. So polygons are similar if they are the same shape but differ in size, right? So congruent polygons will have the same sides, so the sides will be the same. So meaning also to have the same shape. So congruent polygons will automatically be similar, right? So, but polygons, the only requirement for them to be similar is that they must have the same shape. They don't have to have the same size. So we will deal about, of course, angles. Shape, I mean, has to do with angles. And proportionality between sides. So I write it out clearly here. Two polygons with the same number, so hashtag is for number, with the same number of sides, two polygons with the same number of sides are said to be similar. So they are similar if all pairs of corresponding angles are equal. So this is that equiangular. So, and all pairs of corresponding sides are in the same proportion, right? So what does it mean? All pairs of corresponding angles are equal. It means, so if you were to look at these two polygons, AEDCB and PQRST, or ABCDE, PQRST, two polygons. So we claim that these two polygons will be similar if angle A, if that angle A is equals to angle P, right? And angle B is equals to angle Q. And angle C is equals to angle R, angle D is equals to angle S, angle T is equals to angle E. So that's what we mean by that. Triangle ABCDE is similar to polygon ABCDE is similar to polygon PQRS if those angles are equal. And so you must satisfy two conditions for polygons. For triangles, it's okay to satisfy one, either the angles or the proportionality of sides. But for polygons, you must satisfy both the angles and the sides. So second condition is that AB over PQ should be equal to BC over QR, which is CD equals to CD over RS, which is equals to DE over ST, which is equals to EA over TP. So that is the conditions. So I'm not going to bother proving that, but just know that these are important. So I will just say NB. So these two are important. NB. Two conditions for polygons. Angles and sides. But for triangles, it must be one of the two. Okay, so here's a quick exercise. If you have this polygon you are given that you are told that PQTU is similar to PRSU. Polygon PQTU is similar to PRSU, and the question is, what is X? Can you quickly find X? Okay. So what do we know? Because we are told that these are similar polygons. So if the polygons are similar, we expect that PQ all over PR should be TU or UT all over SU. So PQ over PR should be TU over UT over US, which is that. And what do we know about this? What is PQ over PR? PQ is X. And what is PR? PR should be that whole, so it is that whole side, which should be X plus 3 minus X. So it's basically 3. So X plus 3 minus X is equals to UT is 3 all over SU. 3 plus 1 is 4. So X minus X is 0. So we'll be left with X over 3 is 3 over 4. So therefore, X is 9 all over 4. So we have solved for X in this polygon using similarity, using what we know about similarity. That if PQTU is similar to PRSU, then that should be the case. The proportionalities of the sides. Okay. Okay, this is the last page. You can see here is where we started. So this is the last page. Thanks for enjoying. So here we are given. So this is just. I'm just want to demonstrate the similarity idea also now, because I've just used it now using polygons. And let's just use it for one case for triangles, right? So if you are given a triangle ABC and another triangle DEF with, right, you are told that, I mean, it can be that has to be AB. With AB, it should be AB, I think, AB all over DE. AB, yeah, this should be DE. I think I made a mistake here. AB all over DE should be equals to AC all over DF, which should be equals to BC all over EF, right? So this is a given. So we are given that in triangle ABC and triangle DEF, you have these proportionalities being the same. AB all over DE, AC over DF, BC all over EF. And what are we required to prove? We are required to show that if this is the case, remember I said for triangles you need two, for polygons you need two conditions, but for triangles one is sufficient because one might imply the other. So if you are given that you have similarity, you have proportionality, equality, then can you show that then it follows that the angles are equiangular, right? So we're going to use similarity of triangles. So what do we do? So the first thing, I've constructed GH. So I've drawn GH, right? So construction. Okay. So from here, what do we know? From drawing GH, what we have now by construction is that AG should be equals to DE, because this is by construction, right? we've constructed, so we are given this triangle DEF, but we were given ABC. So we construct GH such that AG is equal to DE. Okay? So we move on. So what else do we know? We know also that AH is equal to DF. This is also by our construction. So what will we have here? We will have that just by having these two, AG being DE and AH being DF, this will mean therefore GH should be parallel to BC. Why? Because these are sides in proportion. So these sides are in proportion. GH should be parallel to, because this is by this, we also constructed it like this. GH to be parallel to BC. Because that's how we've drawn it. So this will imply therefore that angle B is AGH. So angle B also is AGH because of the corresponding angles of parallel lines. And you also have angle C being equal to AHG, similar reason. And with that, then you have triangle AGH, which is that top part, being similar to triangle ABC. So if you have shown similarity, so we've used this construction to show that we have, so if there is similarity, then this implies equiangularity in triangles. You understand? So we've shown that since we are given this, we can show that triangle AGH and triangle ABC are similar. Therefore, they must be equiangular. And we can also show this for triangle ABC and triangle DEF. These will also, using the same procedure, you can show for triangle ABC and triangle DF. Here we're showing for AGH and ABC, but you can do the same for that. And if that is the case, if triangle ABC is similar to triangle DF, therefore angle A must be equal to angle D, and angle B must be equal to angle E, and angle F must be equal to angle C. Right? So that is what must happen. So lastly, just to apply this proportionality of sides, if you are given a polygon PQRS and you are told that PQRS is a trapezium and PQ is parallel to RS, and the question is prove, so you are required to prove that PT multiplied by RT is ST multiplied by QT. This is what we are required to prove. But we are told that PQ is parallel to RS. Right? PQ parallel to RS. Therefore, you can say in triangle PTQ, which is PTQ, and triangle STR, you have angle P1 being equal to angle S1. Why? These are alternating angles because PQ is parallel to RS. So look at P1. There's P1 there. P1 is that. And our claim is that it is equal to angle S1, which is that angle there. You can see these are alternating angles between parallel lines. And then another one that you can get is Q1 is R1, similar alternating angles. So Q1 is Q1 must be R1, alternating angles between PQ and RS. So what do you have? You have that this angle is equal to that angle is equal to that angle, therefore this angle must be that. And actually there is a theorem, you can check it out, between parallel lines and the ones that are diagonals like this. So that angle is equal to that angle, because these are angles in a triangle, should be equal to that angle. So I don't know what to call that part, maybe O1 and O2. So I'll say maybe O1 and O4, maybe call that 1, 2, 3, 4. And therefore you have three angles being equal. You have three angles being equal. That is equal to that. So these are equiangular. So therefore triangle PTQ is similar to triangle STR. Therefore, if triangle PTQ is similar to triangle this is, why am I calling it O? It's already labeled as T, so that's T1 and T4. So this PQT and STR, so those are similar. So if they are similar, this means that PT all over TQ, PT all over TQ should be equals to ST all over TR, because of similarity. And you can see, you can just cross multiply. So if you cross multiply, you will have PT multiplied by TR is ST multiplied by TQ. And this is what you wanted to show. This is what I wanted to do. PT multiplied by RT is, and this is correct. So we've used similarity of triangles and the similarity of polygons to show how this idea works. Okay. So I think from here onwards, that should be it for Euclidean geometry. Of course, you need to work more. You need to go through this again. All the best with your studies. God bless you. We will continue supporting you, I think, maybe from my side with maths and physics for the coming 4 or 5 weeks, and that will be it. So go home, do your work, stay blessed, and keep safe. Yeah, cheers. Bye.